All right, welcome back to Linear Algebra. We're going to finish up our work in section 5.2 and chapter 5 for us by kind of talking about our progress in this diagonalization problem in the context of a more general construction in vector spaces called direct sums. All right, so we'll kind of start off by just sort of recalling what the sort of main summary of our first 2 days of working in section 5.2, that when you're given some linear operator on a finite dimensional vector space called T, that operator is diagonalizable if and only if there's sort of two conditions you have to check. First, that the characteristic polynomial of the operator splits over the field. So it has to factor into a product of linear factors, possibly with some of the linear factors repeated. So they don't have to be distinct, but it does have to completely factor into linear factors. Okay, each one of those linear factors gives rise to an eigenspace, yeah, which we denote by E lambda I, and the dimension of that eigenspace has to be the multiplicity of the corresponding eigenvalue. So if a factor like T minus lambda to the M shows up in our characteristic polynomial, then the eigenspace that goes with that eigenvalue lambda has to have dimension M, and that dimension has to be full for every eigenvalue for it to be diagonalizable. Remember that eigenspace is just the dimension of V minus the rank of the corresponding operator T minus lambda I times the identity operator. All right, so that's kind of a summary of our work so far. So in order to put that in the context of this stuff called direct sums, let's make the following definition. So if you take a bunch of subspaces later on in the lecture, I certainly have in mind that these are going to be eigenspaces, but this is kind of more general, so I'll state it this way. You take a bunch of subspaces, then if I write their sum like this, the sum of the subspaces, which written out in longhand could be written like that, W1 plus so on. What do I mean by it? I mean it's the set of all sums, W1 plus W2 and so on up to WK, where the condition is that each one of those summons, WJ, has to come from the corresponding subspace, capital WJ. Okay, so you literally just look at the collection of all vectors that you can get by adding things where each one of the terms in your sum comes from the subspace WJ. So that's just simply called the sum of the subspaces. All right, I'm going to leave it as an exercise to you that if WJ is a subspace for every J, so is this sum. That collection would have the zero vector, it's closed under sum, it's closed under scalar multiple, it's a reasonable exercise. So the sum of subspaces is a subspace. Okay, so continuing here, if you take those subspaces W1 to WK, and if that sum is the entire vector space, okay, so when you sum them up, you get everything, and you take any one of them, so for any j between 1 and k, you intersect that one with the sum of the others, right? So notice here in particular that I'm summing over the indices I that are not equal to j. If that intersection is always just the zero vector, and here I'm kind of maybe being slight, I mean, it is zero, the subspace, but technically speaking, this is a set. So if you want to put set braces around that, that's fine. So if that's the case, then I'll call V the direct sum of the WJs, okay? So V is a direct sum of the WJs. If one, it's a sum, so everything in V is expressible as a sum of the vectors in the W's. And two, they're kind of independent in the sense that if you intersect any one of these subspaces with the sum of the other ones, they have nothing in common except the zero vector. So when that's the case, we'll call this thing the direct sum. The notation for it, because we've already used plus for sum, we use these circle pluses. So this circle plus is called the direct sum notation. And you can also write that in kind of shorthand if you like. I won't do it in this lecture, but you might see it in books. People just kind of use the same spirit. You can write it's the direct sum from 1 to k of the WJs. So if you prefer that shorthand notation, I'll certainly understand what you mean by it. Okay, so when you draw the circles around the plus, it kind of means two things. One, that the W's sum up to it, and two, that they're sort of independent in the sense that any one of them intersect the sum of the others is just the zero vector. Okay, super quick example here. Maybe we can look at just a two-dimensional example. If you take V to be R2, take W1 to be the scalar multiples of the first basis vector, say E1. It's the set of things that look like A comma 0. W2 is the scalar multiples of the second then R2 breaks down into the direct sum of those things. Or if you want to write it, it's RE1 direct sum RE2. Okay, why is that true? I'm just going to kind of verbally check it. Clearly, W1 plus W2 is R2. Yeah, every vector in R2 looks like something in the first subspace, A comma 0 plus something in the second subspace, 0 comma B, because the sum of those two things is AB. You want me to write that down? Just saying that any vector in R2 looks like something in that first subset plus something in the second subset. Okay, and if you're in both of those subsets here, the intersection, there's two sets. So if you looked at the intersection of these things, R times E1 intersect R times E2, well, the only thing in there is the zero vector. So they're independent. That gives you kind of a sense of what a direct sum is. Okay. There's a whole topic. I mean, we could spend a whole day talking about direct sums and properties. The author has kind of built most of the important properties into the following theorem. So I want to try to prove this theorem with you guys, give you some experience working with this. So what does the theorem say? It says if you take a bunch of subspaces, W1 to WK, what my acronym means, I'm just going to say this out loud, the following are equivalent. So I mean that if any one of these statements hold, they all hold. And if any one of them is false, they're all false. Okay. So the logical structure I'm going to give in the proof is I'm going to show that the first statement implies the second implies the third, and so on. And then finally, when we get to the fifth one, I'll show that it implies the first one. So if I can show that string of inequalities, or sorry, implications, then we will have proved the theorem. Okay, so you might have to either refer to your book, because as I start scrolling, you're not going to be able to see these things anymore, but so I can try to leave them visible as we start our first proof. Let's try to prove that the first condition implies the second. So let's suppose the first condition, that is, let's suppose V is the direct sum of the W's. And then what am I trying to show? I'm trying to show the second condition. So I want to show that V is the sum of the W's, and that if you take the sum of things, each one of which is in Wj, and get 0, each one of the things had to be 0. Okay, so the only way you can add things in these summons together and get 0 is if you started with 0 in each summand. Okay, so let's suppose that V is a direct sum of the W's, and suppose that we have this sum equal to 0, where each summand comes from the corresponding subspace. All right. Well, if you sort of just algebraically rearrange that equation, pick a j between 1 and k and solve that equation for wj, well, there's minus signs because I took them to the other side of the equation. It's minus w1, minus w2, and so on, skipping wj, right? Because wj I left on the other side of the equation. And that thing, by definition, is an element of wj. Why? Well, because it equals wj, and that comes from that. But it's also an element of the sum of the other things, because each one of these other elements is from those other ones. And any linear combination of them is in this sum. All right, because if W1, for example, is in capital W1, so is its opposite, because it's a subspace. Well, but we said that this is the direct sum. So this intersection consists only of the zero vector. Well, so in particular, then Wj has to be 0. J was arbitrary, so that proves 2. Okay. So again, get out your book and look at the statement of the theorem, because I'm just going to assume that you have it in front of you. So let's try to assume the second condition and deduce the third. So, okay, well, what are we trying to prove in the third condition? What am I trying to prove in the third condition? That every V can be written uniquely as a sum of those W's. Okay, well, since we're assuming that V is the sum of the W's, certainly given a vector in V, we can write it that way. That's because it's the sum of them. So we just have to worry about the uniqueness. A uniqueness proof always starts the same way. Suppose you've done it some other way. I put some tildes over them, W1 tilde, WK tilde. Each one of those WJ tildes also comes from WJ. Okay, well, that gives me two expressions for V, right? V is equal to the sum of the W's, V is equal to sum of W tildes, set them equal to each other and subtract, and you get the expression the sum of the differences is equal to 0. But each one of these things, W1 and W1 tilde, come from capital W1, so is their difference. It's a subspace, and so on. Each one of these things would be in the appropriate subspace. but by hypothesis, if you add a bunch of things in these subspaces and get zero, each one of the things is zero. So sorry, that tilde should be a minus sign there. So the difference, wj minus wj tilde, is zero for every j, and that means that the w's and the w tildes were the same. That's the uniqueness. Okay, so now if we suppose that everything can be written uniquely, what do I want to prove in number 4? I want to prove that if you take a basis for each subspace wj, the union of them is a basis for the whole space V. So let's let W beta J be a subspace for the a basis rather for the subspace WJ. Do that for every J. And then if you give me some V, right, by the hypothesis in 3, I know that there's a bunch of vectors, one in each subspace, that V can be written like that. Okay, that's by the assumption 3. It's my hypothesis. So every wj is certainly in the span of the basis beta sub j, because it's a basis for that subspace. So if V is a linear combination of things that are linear combinations of those betas, then V is in the span of those things. So the set beta, the union of the beta j's, spans V, is where we're at in the proof. So we need to show that beta is linearly independent. Okay, so let's give ourselves some notation. Let's suppose that the jth basis beta j has things in it that are called Vij, where I goes from 1 to something that depends on j. I'm calling it n sub j. Okay, so in my notation here, I'm just saying that n sub j is the dimension of the jth subspace. All right, and let's suppose that we have a bunch of scalars. I'm going to double index them, aij. They're scalars in F. And the sum, well, as I goes from 1 to n sub j, and j goes from 1 to k of those basis vectors in beta, the union of the beta j's, suppose it's 0. Okay, so looking at this sum, just sort of fixing a j and summing over the relevant i's, let's call that thing wj. Wj is an element of capital Wj because the Vij's are in there. It's a subspace. So by star, if you look back up at star, the sum of those little w's is 0, right? The sum of those little w's is 0. We're assuming that you can only write a vector one way. It's the uniqueness. It's our assumption in this condition 3. But there's another way to write 0 as a sum of things in the wj's. You can just write it as 0 plus 0 plus 0 and so on. Zeros in every one of those subspaces. So by the uniqueness in our hypothesis, each one of those wj's actually has to be 0. Okay. So if we look back up here at what the wj's are, they're linear combinations of things in beta j. Beta j is linearly independent because it's a basis. So that actually forces all those coefficients to be 0. So that shows that this set beta is also linearly independent, and hence it's a basis. Cool, it's going pretty smoothly. Let's try 4 implies 5 is trivial. If you look back, 4 just says that if you have a basis for each wi, then the union is a basis for v. 5 just says, well, for every I, there exists a basis for wi such that their union is a basis for v. Of course, wi has a basis, it's a subspace, so 4 implies 5 is just trivial statement. So we can finish the proof by showing that 5 implies 1. So let's assume 5, that there's a basis beta j, excuse me, for every wj. And we're assuming that the union of those things is a basis for v. And what do I want to do? I want to show v is the direct sum of the w's. So I want to show that sum is v and that intersection equaling 0 property holds. All right, so if you give me any v, I can certainly find a bunch of scalars to write v in terms of those vij's because beta is a basis, right? And I'm going to group the same way. If I fix a j and call that thing I just wrote brackets around wj, then I've written v as a sum of wj's where wj belongs to the jth subspace. Okay, so what does that show? That shows, oops, wrong color pen. That shows that v is a sum of the w's, not a direct sum, but that every vector in V can be written as a sum where each summoned is in the corresponding subspace. Nice. So now I have to worry about the intersection thing. So suppose that I took some vector v, and it's in wj, and it's also in the sum of the wi's where I isn't j. All right. My goal is to show that this thing is 0. I want to show that v is equal to 0. So let's just look at what we've got. I'm going to use similar notation to what I did above. If v is in wj, I can write it as a linear combination of the beta sub j basis vectors. Those beta sub j basis vectors are things that look like vij, where I goes from 1 to n sub j. All right, that's because beta sub j is a basis. But if v is in the sum of the other w's, well, it can be written as a sum of little w's, but not using the jth one, right? So I'm summing over i's, but the I is not equal to j. So notice that I'm skipping over the jth one. It goes from j minus 1 to j plus 1. All right, well, those two expressions for v are equal to each other. First, actually, before I say that, let's take each one of these wj's, so these wi's, w1, w2, and so on, except for the jth one, let's write them as linear combinations. So the beta sub i's are bases, right? So there have to be some scalars. I'm talking about I not equal to j. That wi is some scalars times the basis vectors. So these things come from the basis beta sub I, right? So that's just because of the fact that they span. Okay, so if we kind of lump all of that in, I've got this expression for v, I've got that expression for v. So if I set them equal to each other and subtract, I'm going to take the one that I'm double underlining to the other side of the equation. So it's got minus signs. Okay, and then here's the other one, the single underlined one. And that linear combination is all equal to 0. But what's that a linear combination of? It's a linear combination of these V's, VLJs, where L is either J or some I that's not equal to J between 1 and K. So that's a linear combination of the basis vectors in beta. But we're saying beta is a basis for V, so those coefficients all have to be 0. Beta is a basis, so those coefficients all have to be 0. So in particular, the coefficients in the double underline thing are 0. That means that Vj is 0, or sorry, that V is 0, right? So the only element of that intersection was 0, and that shows that our sum is direct. Cool. That was talking fast. I hope you stop the video and kind of process it. Okay, so we're going to end this by saying, like, well, why bring this up right now? This direct sum just kind of gives us a different language to describe these eigenspace decompositions. Remember, we've already proved in theorem 5.9 that if an operator is diagonalizable, then if you union together the basis vectors for any one of its eigenspaces, you get a basis for the entire space. In fact, it's if and only if. The only way an operator is diagonalizable if that happens. So this theorem 511 is really just a translation of that into the direct sum language. So if you take an operator, and let's suppose that its distinct eigenvalues are called lambda 1 through lambda k, the statement is that that operator is diagonalizable if and only if V is a direct sum of the eigenspaces. Okay, so this is just translating into this new language, although it's certainly important for you to learn the language. So I hope you'll slow down and study this proof carefully, but let's look at it. So suppose T is diagonalizable. Okay, for every one of the eigenvalues, lambda 1 through lambda k, let's let beta j be a basis for the corresponding eigenspace. So like I just said, theorem 5.9 says that if you union those bases together, you get a basis for V. Okay, so by the theorem that we just proved, if you have bases for a bunch of subspaces and you union them together, then V is the direct sum of those subspaces. That's by the that's by the implication 5 implies 1. Okay, so if you have a bunch of bases for subspaces and they union together to give a basis for the space, then V is a direct sum of that collection of subspaces. So that's by theorem 5.10, and in particular, it's the implication the fifth part implies the first part. Cool. Conversely, if V is a direct sum of those eigenspaces, again, if we let beta j be a basis for the jth eigenspace, J is a number between 1 and K, then again, by theorem 5.10, if you union those bases together, you get a basis for V, right? Because V is a direct sum of these things. But then that basis, beta, would be a basis consisting of eigenvectors. And so by theorem 5.1, your operator is diagonalizable. Okay, so there's a little bit of just structure in order to describe this. When is an operator diagonalizable? Precisely when its eigenspaces form a direct sum decomposition of the entire space. All right, thanks for listening.